O professor Donato, então, ele fez a sua graduação em Física, lá na Universidade de Oxford, na Inglaterra, né? Mestrado em Física também em Birmingham, Estados Unidos, e depois doutorado em Física na Universidade de Arizona, também lá nos Estados Unidos. Teve passagens aí, né, como pós-docs em vários lugares, né, ao redor do mundo, passou pela Universidade de McGill, no Canadá, em Goethe, na Alemanha, Colômbia e entre outras, né. Ele agora é professor da Unicamp, né, pelo que me disse aí, desde 2014, e é especialista na fenomenologia de colisões ultrarrelativísticas de íons pesados, trabalha também com hidrodinâmica relativística, mecânica estatística relativística, QCD e sistemas fortemente correlacionados. Então, Donato, mais uma vez, muito obrigado pelo aceite. Fica à vontade, qualquer coisa eu estou aqui, é só chamar.
Muito obrigado para vocês todos de estar aqui. Eu não vejo vocês a causa do formato do talk, mas sim. Obrigado para chegar a me ouvir sobre uma coisa que é um pouco não é minha atividade de pesquisa principal, mesmo sendo relacionada. Espero explicar para vocês de onde está a relação. É um seminário muito especulativo, mesmo que eu gosto dessa coisa, mas é bastante especulativo. Claramente, por favor, se você tem dúvidas ou comentários, por favor, me interrompa, é uma coisa muito informal. É baseado em uma publicação, é também uma publicação que escrevi, não pus no archive, mas submeti no jornal. Actually, I'm sorry. Just as an important thing, I prefer to talk about this physics thing in English, if everyone is okay with this. If everyone is okay with this. I mean, as you can hear, I speak Portuguese, but I'm more comfortable speaking about in English. But if people really want to, I can of course speak Portuguese. Yeah. So the point here is that I would like to convince you that the study of quantum gravity, it's not entirely hopeless to have an experimental program in the study of quantum gravity. And in fact, we might be coming to somewhat of a golden age, and I will explain why. And it will make contact. The reason that this is exciting is that it will make contact with the original reason as to why the study of quantum gravity was considered to be non-trivial. I mean, which goes back to a paper from the 1930s. And I will explain maybe one way in which this question from the 1930s can be tackled. And then I will sort of speculate as to what an effective theory of quantum gravity might look like, which, if the experiments that are being planned will give the answer that I think it will give. If you're really interested in what we're doing, I would just like to say that we're actually going to have a conference about it. So it is speculative, but it's not crazy. The definition of not crazy is people will come from all over the world to São Paulo to discuss this. This conference will be in the last week of September at the Institute of Theoretical Physics and at the ICTP of São Paulo, and the website is here, and please contact me if you're interested in attending. So, quantum gravity. The usual problem that people have, whether you're a practitioner or a practitioner from another area of physics who thinks that this is all crazy, is that it's just theory. The main problem is usually talked about as one of mathematical consistency. I mean, basically, quantum gravity is non-renormalizable. And the experimental data is either non-existent or very hard to sort of play with. There is the cosmological constant problem. So naive theoretical estimates are off by 50, 120 or 50 orders of magnitude. But this is something that is difficult to investigate further beyond, there seems to be dark energy and there seems to be tension. It's not something we can play in the laboratory with. And the good reason for this is that quantum gravity is supposed to arise when gravity becomes strong, as when the separation of scales, as with good non-renormalizable theories, happens, and that's at 10 to the 19 GeV, the Planck scale, which is, you would need a collider with the solar of the size of the solar system, and this will probably never going to happen, certainly within our lifetimes. On the other hand, if you stop thinking about JeV, this is actually the mass of a milligram. The problem is that usually masses of a milligram are classical, they're not quantum. But there is other things that one can do than putting this mass of a milligram concentrated in a collider energy. So one can at least play with a few things. And in fact, there are quite a few ideas on how to investigate quantum gravity experimentally. You have high energy cosmic rays, which might give you a breakdown of sort of special relativity. Precision multi-messenger astronomy could give you an effective Lagrangian, which is different from GR. You have analog gravity in that there is a profound analogy between gravity and hydrodynamics. And I will come back to this analogy towards the end of the talk. And finally, if there is quantum gravity, then the quantum noise field theory background of gravitons might be seen in big systems like Bose-Einstein condensates or dark matter detectors, where you might be able to see sort of spontaneous collapse and spontaneous decoherence. And Nature was published about it by some of the people who will come to the conference in September. And finally, we actually have been learning how to put things which are less than a milligram in quantum superpositions via nanotechnology. And this is sort of what I would like to concentrate. It might be that this is sort of a promising avenue. The main idea was actually due to Feynman in the 50s, but at the time it was really a Gedanken experiment. You take two masses and you put them in two interferometers. Each mass goes into an interferometer with a beam splitter. And the point is that this is going to be a superposition between a path in which the masses are close, that's basically the path in which M1 goes to the top and M2 stays at the bottom arm, and a path in which they're far away. That's the path where M1 stays in the bottom arm and M2 stays in the top arm. And textbook quantum mechanics basically says that these two gravitational masses attract each other. And if they're really quantum, so if gravity is quantized, then the difference in energy between the two paths, because of their mutual gravitational interaction, is going to introduce a difference in phases. We're talking about a completely minuscule energy. This isn't gravity of the Earth with the nanoparticles, or even of the detector of the nanoparticles, but this is the mutual attraction of the nanoparticles. So the mutual attraction of 2 milligrams. So this is tiny. However, we've also been really good at these precision measurements, and all we need is, for example, a clock, because energy propagates as time, the phase difference is time, so we need to measure time really, really precisely. And for example, we can, if these nanoparticles have spin and spin processes, and we can collect millions of these events in which they pass through the interferometer this way, then we can measure the time difference. Then we can measure the precession time difference. And I am not an experimentalist, but there are experimentalists with nanotechnology who work on these nanotechnology setups who say that something like this might be possible. If this phase difference is experimentally proven, as far as I'm concerned, we're there. Because this phase difference is exactly what a graviton is. A virtual graviton projected into the time component of the graviton is a spin 2 object. It's a symmetric matrix. It's a virtual graviton projected to the time component is basically what this energy difference is. And if you have virtual gravitons, then by quantum field theory unitarity, you're going to have real gravitons, and we know that gravitons are spin 2 independent. So as far as I'm concerned, the positive result of this experiment is the experimental proof that gravity is quantized, and a vehicle to sort of study gravitons as quantum objects. Just to say that this interferometry was sort of the first and the most obvious idea, but for example, there is a very similar thing here. You have two rotors, which are quantum. You have cavities, and if the rotors gravitationally attract, there is going to be a phase difference in the cavities. There is going to be an extra dilation inside the cavities. So basically, I mean, Feynman was talking about these setups in the 50s, but now it's not theorists talking about this. This is most of the people who will come to our conference are nanotechnology experimentalists. I mean, they're really people who don't waste their time and who do things which make a lot more money, if you want. So this is, there is a realistic hope, at least, that these experiments are doable within our lifetimes. So this is really exciting. This is really exciting. Will we see black holes in our lifetime at the LHC? We haven't seen them, but this is sort of an alternative. Which is also a good time, given this, it's also a good time to remember back in the 30s, the original non-trivial paper about quantum gravity. It's also good, just for your historical knowledge, to remember Matvei Bronstein was a brilliant, completely brilliant, virtually unknown figure. Part of the reason that he's unknown is because he was arrested and shot by Stalin's secret police 2 weeks after defending his PhD thesis. And this, of course, cut off his career. There is a great biography of him by Gennady Gorelik, both scientific, it goes into detail about his work, and sort of human, because he also wrote great science popularization books. So anyway, he was actually originally a semiconductor physicist, but he got bored with semiconductors, and he was asked a very simple, so he was like, I want another PhD project, and he was given the project, here's something really simple, quantize gravity. It's easy. I mean, Heisenberg and Pauli quantized electromagnetism, you quantize gravity. It's spin 2 instead of spin 1, and it's spin 2 instead of spin 1, and at least sort of gravitational waves, you basically repeat the Heisenberg and Pauli QED quantization with more matrix components. Except he also got talking to Landau, and Landau told him that this is all nonsense because quantum fields are nonsense, because something cannot fluctuate and be locally defined. This is something that Landau strongly actually believed throughout his career. So he got into these sort of semi-philosophical discussions, and he produced a paper that sort of said, well, all of you are kind of right. Quantum field theory is problematic, and it sort of still is, because it is true that something localized at every point cannot fluctuate. However, I mean, you know, other people were thinking about this. Bohr and Rosenfeld talked about compensator charges, and this is sort of where renormalization comes from. But there is an extra problem. The problem is that the detector, if the field is localized everywhere at every point, it's impossible to isolate the detector from the system. And this will produce a detector system back reaction. This is, by the way, also true for quantum mechanics, but quantum field theory is even more true because of the fact that quantum fields are localized everywhere. But Bronstein said this is actually not too much of a problem, because the detector system back reaction is proportional to the charge over mass ratio. The detector couples to a system via charge. The detector has a mass. And as long as the charge over mass is infinitesimally small, detector back reaction is infinitesimally small, and you will reproduce the canonical quantization relations. And you will reproduce the canonical quantization relation. You just need a big detector with respect to the de Broglie wavelength over typical fluctuations, and you need a massive detector with respect to the energy. And you see the problem for gravity, and it's specifically a problem for gravity. Because of the equivalence principle, charge over mass equals 1. And therefore, detector system back reaction is never negligible. It's always of the order of what you're trying to measure. Bronstein basically said in 1934 that to remove these contradictions, you would have to quantize geometry, and I don't know how to do this. However, this was a remarkable paper in many ways. In many ways, it's sort of one of the last papers that said something definite and non-speculative about gravity, because it's really an issue. It's amazing how little the specific issue was actually tackled. It's different from non-renormalizability because it's a system detector interaction. It's different from renormalizability, scale separation. This is system detector interaction. But the point is that his speculations about quantum geometry are premature, because all that he was talking about is that the system is not completely quantum and the detector is not completely classical. And we need to put this into account. And since his time, this is actually one area of quantum mechanics where we've made progress. I mean, the issue is, the quantitative issue is that every interaction of everything with everything exchanges energy momentum. So for instance, the nanoparticles in the setup pass through the beam splitter, they pass through the magnets, they pass through the Stern-Gerlach things, and all these things are massive. If these things are light, you are going to have recoil, and recoil of quantum particles with sort of classical detector components introduces decoherence. That's no problem. You make them heavy and there will be no recoil. But by the equivalence principle, mass is gravitational charge. So once again, the experiment is going to exchange gravitons, if you want, with the nanoparticles. And this is tiny, but it's a bigger effect than the nanoparticles. And again, it introduces decoherence. And in both cases, both for a heavy experiment and the light experiment, the decoherence is of the order of the effect you want to measure. So what does this mean? Well, so what does this mean? It doesn't actually mean that gravity is not quantized or anything like this. It just means that we need to make a theory in which the system is not fully quantum and the detector is not fully classical. Very similar conclusions, by the way, were given by people who sort of who thought about this for longer than me, and on a higher level than me, and they published a Nature about this. There is this thing called quantum reference frames. I mean, it's the study which has become pretty important. I urge you all to read their paper. And the basic idea that they point out is that if the equivalence principle is exact and you have a superposition of metrics, you can always go to a co-moving metric, and you will transform a superposition of metrics into a superposition of detectors. But of course, canonical quantum mechanics that we all learn at university doesn't have detector superposition. Detectors are classical, they're not quantum. The system is quantum and the detector is classical. So once again, the point isn't, we are not abandoning quantum mechanics. We're simply saying that we're simply trying to think about what happens when the system is big enough or the detector is small enough that neither are perfectly quantum and perfectly classical. And actually, there is nothing particularly speculative about this. If you look at the lectures of quantum mechanics of Steven Weinberg, he basically says that one of the things that really bugs him is that the wave function is given this oversized importance as the central object of quantum mechanics. The central object of quantum mechanics should be the density matrix, not the wave function, because what we actually measure is sort of traces of the density matrix with operators. And the density matrix can also accommodate exactly the sort of systems that we are thinking about here, open quantum systems, which both the system and the detector is. So there might be no quantum gravity state, but there is no reason that we shouldn't construct a quantum gravity density matrix, which is mixed all the time. The way we do this is like this. You have the system and you have the rest of the universe, and you have two density matrices to put to describe them, and you concentrate on the system. So you trace out the rest of the universe, and you calculate every operator by doing this tracing out thing. It's just that computationally, this is generally very difficult to do, and we don't have a universal recipe, because open quantum systems, you have to look in detail how the system and the detector interact. But we do actually have something close to a recipe, because the density matrix is related to the partition function. And the partition function we know how to calculate using path integrals. And there is actually quite a lot of stuff that we can do systematically. In particular, we can rewrite Bronstein's objection as an effective theory, as an effective field theory. What's an effective theory is when you expand around the action. You have a big part of the action and a small part of the action, and you do this in terms of sort of scale separations. And the scale separation is sort of the openness of the system detector interactions. So what you do is you make a Lagrangian for the system, and you also make a Lagrangian for the detector, and you make them interact, and you describe your observable via source. In particular, for the interferometer experiment, we can actually make a simple but surprisingly realistic model. I mean, it's sort of a spherical cow. The big issue is that usually sort of these decoherence and open quantum systems and superpositions are done using discrete branches of the wave function. So you have left arm of the interferometer and right arm of the interferometer. But a gravitational attraction sort of exchanges a continuum amount of momentum. So we cannot do that. We need an interaction that doesn't just go left arm, right arm. We need an interaction that sort of exchanges momentum. And solid walls and solid beam splitters and stuff like that are very difficult to describe in terms of functional integrals. So we kind of have to think about a spherical cow type approximation. The way sort of one can do this is basically eliminate the detector, eliminate the walls, and eliminate the beam splitters, and substitute all of them with scattering. So instead of a beam splitter and instead of mirrors, you have sort of interacting balls with some kind of potential. And the nanoparticles are other balls. And the way you don't have walls, but instead of walls, you sort of trace over everything outside a certain angle. You trace over everything outside of a certain angle. Physically, sort of, you're approximating the interferometer by a system of obstacles, a system of scattering obstacles. And you are using the detector trigger in particle physics language to eliminate all events, where the balls are not going into the trajectories which are defined by the detector of the wall. The big difference between this and a realistic thing is that you will need a lot more events in this theoretical setup. But once you do the reweighting, you should get the correct answer. So this is sort of what I want to do. I want to approximate the two interferometers by sort of a scattering experiment, and I want to trace out the angles. And the rest is actually sort of simple. Because the gravitational field, we're dealing with non-relativistic systems, so we don't need general relativity. We basically need a Poisson equation with a scalar potential. And the scalar potential is nothing else but the 0, 0 component of the graviton. but the 0, component of the graviton. So the Lagrangian is going to be the non-relativistic Poisson equation. The interaction is going to be the source term of the Poisson equation. And we're assuming that nanoparticles are delta functions. We're assuming that the nanoparticles are delta functions. And where we are going forward is that this is a quantum field. This is a very simple quantum field. And then you have the detectors are not a field, but they're a quantum mechanical source. The detectors are not second quantized. We know that there is 2 nanoparticles, and we know that there is 2 interferometers. So, however, we are considering, and with functional integrals we can do this, we are coupling the detectors and the nanoparticles via these J's, and we're considering the nanoparticles to be first quantized systems, and we're considering the interaction nanoparticle detectors to be delta functions. M and BS is mirror and beam splitter. M and BS is mirror and beam splitter. I equals 1, 2 are nanoparticles. The interaction between them is a delta function, and then you are going to read off the position of the nanoparticles using source terms. Summarizing, we have a Lagrangian which has a free field term, the source terms of the detectors and the nanoparticles, and the interaction between the field and the nanoparticles, and also interaction between the field and the detector components, and the interaction between the nanoparticles and the detector components. Both the detector is sort of a semi-classical first quantized system, the field is second quantized, the nanoparticles are a non-semi-classical first quantized system. And so everything all of the Bronstein objections are self-consistently put in. And believe it or not, this system is actually analytically solvable. There is a very nice textbook that explains how to do this. The reason it's analytically solvable is because you can because you can reduce if you have propagators of a free theory and a delta function potential, you can solve the system exactly. You can renormalize the propagators into a delta function potential. And of course, once you have the propagator, you have the whole, and you have the sources, you have the whole partition function. It can be solved, and it's messy. I mean, what you need, it can be solved, but it's a pretty complicated system. It can be solved, but it's a pretty complicated system, because by the time that all the interaction potentials are nanoparticles and detector components, but there is quite a few interactions. There is the gravitational interaction between the nanoparticles, and there is the interaction between the nanoparticles and the detector components. And once you put everything in, these Green's functions become pretty messy. And also, what you actually need to calculate is pretty messy, because if you remember, we've substituted the interferometer by a sequential scattering and event averaging. So the delta function potentials basically mean that scattering happens isotropically, but we're only going to consider scattering, which lets the nanoparticles follow the trajectories of the detector. Nanoparticles following the trajectories of the detector. To do this, we have to construct wave functions, if you want, states, which are superpositions of the detector components, and we have to trace over everything else. And this is the exact expression, and it's going to be a pretty messy differentiation, but it's going to be a pretty messy differentiation of an exactly solvable partition function. So this is exactly solvable, but as I said, this is sort of a hobby. This is not what I get paid to do. I didn't solve it yet. So I'm talking about this, and I'm talking about this prematurely. But you immediately see, if you just look at these, if you paid attention to the integrals and you paid attention to the form of the Lagrangian, you immediately see that Bronstein's original argument essentially means that the interaction between the detector and the system, so the back reaction of the detector of the system, is always of the same order as the quantum gravity effect, is the same order as the quantum gravity effect. The reason is that the interaction between the nanoparticles, the inertial interaction between the nanoparticles and the inertial interaction between the nanoparticles and the system is of the order of the mass. The gravitational interaction between the nanoparticles is of the order of the nanoparticle mass, which is small m. The gravitational interaction between the nanoparticles and the system is of the order of big M. And the inertial interaction between the nanoparticles and the detector components is the inverse of big M and little m. So basically, if the masses are going to be small, if the detector components are light, Lj is going to be quantum, is not going to be semi-classical. If the interaction components are going to be heavy, then Lint is going to be semi-classical in this Lagrangian here. Lint is going to be semi-classical in this Lagrangian here. And in both cases, the effective theory, the goodness of the effective, if you regard quantum mechanics, the canonical quantum mechanics we learn in textbooks of closed quantum systems, as an effective theory where you disregard the interaction between the detector and the system, in the formalism that I developed, this is going to be equivalent to the statement that the partition factor approximately factorizes into the detector one and the system and the rest and the system one, and the system partition function is much smaller. So the semi-classical action of the partition function is much smaller than the semi-classical action of the detector. And this is simply never correct. This doesn't actually mean that the experiment is, I suspect this basically means that the experiment will always be negative, but I cannot really quantitatively prove it. All that I suspect is that the detector system back reaction is always of the order of the phase difference of the effect that you're trying to observe, which is the phase difference triggered by the gravitational self-interaction. Summarizing, I suspect what I would say is that if the experiment finds a positive result, so if the experiment really finds a phase difference of the order of the mutual gravitational attraction of the nanoparticles, in a sense, you will rule out the equivalence principle in the quantum regime, in the sense that you will rule out the general covariance with respect to quantum reference frames. And the reason is, I could go into detail in this and the reason is that this is going to mean that if you put this system, so if you put this system in a frame which is co-moving with the nanoparticles, if you put the system which is, if you put yourself in a frame which is co-moving with the nanoparticles, you're going to have a superposition of two non-inertial reference frames where energy is not conserved. And there is simply no way that this delta phi is going to be covariant with respect to such a transformation. On the other hand, if it turns out that this phase difference is much smaller than the gravitational attraction of the nanoparticle, or the experiment sort of gives not necessarily a negative result, because as I said, I haven't really quantitatively calculated this. But if it turns out that the experiment is best described by a mixed quantum classical system, and if it also turns out that other tests of the strong equivalence principle, seem to show that the strong equivalence principle works, then we might start thinking about an effective theory where the equivalence principle is exact. These other tests are not quantum. They are classical tests. But actually, the strong equivalence principle has been demonstrated. The strong equivalence principle has been demonstrated to a surprising accuracy by things like the Nordtvedt effect. So for those who do not know, the Nordtvedt effect is the idea that if the inertial mass of a moon, think about the Earth-Moon system, which was originally thought about. The moon's orbit is elliptical. The moon's orbit is elliptical, and therefore the gravitational potential that the moon encounters varies with respect to the moon's orbit. And the inertial mass, you have to subtract the gravitational potential energy. The inertial mass, you have to subtract the gravitational potential energy. If it turns out that the gravitational mass does not change along with the inertial mass, there is going to be a detectable precession of the orbit. And this was actually measured for the moon using the lasers that the astronauts put up there. And it was also now measured using the double pulsar systems. And the equivalence principle seems to hold. Another sensitive, very sensitive test of the equivalence principle, which I should actually have mentioned, is, and I should, this is a good occasion to mention something I should have mentioned before. The reason these experiments are new, there are people who objected. There are people who objected to. There are people who objected to this quantum, to these experiments being quantum gravity, because in the 70s, people already saw the gravitational effect of neutrons, the phase difference of neutrons falling in a gravitational potential. This is known as the Colella-Overhauser-Wagner experiment, cow experiment. They will probably get a Nobel Prize in the next few years. I mean, the experiment was done in the 70s. This is what I imagine. This is a very different thing, because the cow experiment is the interference between a quantum body, so these are the neutrons, and a classical body, which is the Earth. So this is sort of the Schrodinger equation. This sort of experiment really measured the quantization of the gravitational field because it measures the phase difference due to the attraction of two quantized systems. So this is a very different thing. And in particular, the Bronstein objection to the quantization of gravity is completely irrelevant for the cow experiment, but it's not going to be relevant for this experiment. Anyway, so if this experiment, it turns out that the Bronstein objection is going to be significant, and also if the cow experiment has since evolved into very sensitive tests of the equivalence principle because they can measure the difference between the falling rates of fermions and bosons, between basically spins, objects of different spin, isotopes of different spin. And of course, it turns out that so far, the equivalence principle works well. So essentially, I would argue that if this experiment succeeds, then quantum gravity, whatever it is, cannot be written in terms of quantum reference frames. So this, if you look at superpositions of reference frames, you will not be able to transform coordinates into co-moving coordinates and transform the reference frames, a superposition of reference frames, into a superposition of detectors. The system stays quantum and the detector stays classical. On the other hand, if the experiment will give a negative result, and at the same time, the equivalence principle will continue to be experimentally valid, we'll seriously have to think about whether the equivalence principle should be implemented at the level of an exact quantum effective theory. How much time do I have? Hello?
Yes, about 20 minutes.
About
15,
20 minutes.
20 minutes, yeah.
20 minutes, okay, 15 minutes. 15 minutes is all I need. I mean, so how would we do this? I mean, the short answer is that I don't really know. But I have a few suggestions. I don't really know, but I do have a few suggestions. And I have to go back to Weinberg. I mean, because Weinberg is really one of the people who really understood these things. So let's go back to, let's forget about general relativity. Let's go back to special relativity. Combining Lorentz symmetry with quantum mechanics was really problematic essentially because space and time have a very different role in quantum mechanics. Space is a unitary operator, time is anti-unitary operator. How did quantum field theory resolve this problem? It basically said that space and time, neither space nor time are operators. Space and time are labels. Fields are operators. And then you can basically make sure that correlators between fields are covariant under Lorentz transformations. And this was progress. This is sort of one of the last real fundamental paradigm shifts of physics, together with renormalization, in my opinion. What to me was always amusing as an educated outsider who was following the talks is that in most approaches to quantizing gravity, you kind of go back. And there is some prices that came. I mean, neither space and time are observables, only fields and correlators are. States become sort of ill-defined. They become wave functionals, and mathematicians will tell you that these things really don't exist. There are limits of things that seem to exist, and renormalization is basically a study of these limits. But in any case, this was real progress. And most approaches of quantum gravity, and this includes string theory and loop quantum gravity, by the way, in a sense are based on going back, on quantizing space-time in metrics, rather than building on this project. Rather than building on the progress that has been made. And the progress that has been made, building on the progress that has been made would essentially mean inventing a theory where correlators are generally covariant. Because the progress that has been made is all correlators are Lorentz covariant under Lorentz transformations. The next step would be, can we invent a theory where correlators are covariant under general coordinate transformations? I don't know. I don't have a theory like that. I can tell you that the equivalence principle is actually one of the supreme ironies of the world, is that the equivalence principle is required at tree level. It's not just there, it's required. Because if you don't have the equivalence principle, you will not be able to reconcile the fact that virtual gravitons have 5 polarizations and real gravitons have only 2. I mean, reconciling this involves a group of gauge-like symmetries, which to tree level is equivalent to the equivalence principle. The problem is that typically you have nonlinear corrections which break the equivalence principle. And this was done, this was now done by many people. I mean, Donahue, who will hopefully come to our conference in September, is sort of the big specialist in this. Because once again, I mean, the reason why gravity was written in a geometric way, this wasn't an assumption. This was a consequence. I mean, this was sort of Einstein's genius. The assumption is that the strong equivalence principle is exact. The strong equivalence principle is exact. And the fact that you can always describe a gravitational interaction by curved space-time whose straightest, where the path that minimizes the action is the freely falling path, which is curved to the measure of tidal forces. I mean, that's sort of a consequence of this. So quantizing this is difficult because this is typically non-unitary. So this is typically non-unitary. And in fact, there is a very reasonable viewpoint that the equivalence principle just doesn't make any sense in quantum mechanics. It's not just broken, it's ill-defined, because if tidal forces are comparable to the de Broglie wavelength, then there is no way of talking about general coordinate invariance because the particle is delocalized. And with this, I disagree. And with this, I disagree simply because there is a perfectly reasonable definition of the equivalence principle, which is equivalent in the quantum regime, and it's the definition that I gave. All correlators are generally covariant. If you think about it, this definition is exactly equivalent. This definition is exactly equivalent to the definition based on requiring the energy momentum tensor defined in terms of the Lagrangian, the functional derivative of the Lagrangian with respect to the metric, to be exactly the same to all loops, to all orders, always, to the energy momentum tensor as the vertex function of the graviton. Because the energy momentum tensor is the generator of non-inertial transformations, these two definitions are equivalent, and this would be, to me, an acceptable definition of the strong equivalence principle in the quantum regime. I'm not saying that quantum gravity necessarily is invariant under these transformations, especially because I certainly don't have a theory of quantum gravity. But I'm saying that it's a reasonable definition. So I don't agree with the idea that the equivalence principle is useless to think about quantum gravity. It's useful. That's one way of thinking about it. And I can also say one more thing. Let's go. Everything I said everything I said in the first part of the talk, in the experimental part of the talk, is actually a good guide of constructive and effective theory. As I said, the idea, this general covariance plus quantum mechanics essentially says that a unitary canonical quantum evolution is fundamentally incompatible with the equivalence principle. That's true, which basically means that canonical quantization, where you basically build up a quantum algebra under unitary representations and commutation relations, that you cannot do. At least if your operators describe observables. Because your observables will never be purely quantum. Your observables will always contain detector system back reaction, if the equivalence principle is exact. However, if you define things in terms of density matrices, and you give up unitarity, and you replace unitarity, for example, unitarity is important because your operators are complex, and you need a link between the real and the imaginary part. But you can replace it with something else. And here I will just say that we don't just have general relativity as a generally covariant theory. There is a poor people's general relativity, which is actually what I do for a living, what I get paid for, hydrodynamics. Hydrodynamics is not general relativity. There is no curvature term, but it is generally covariant. Its Lagrangian is not locally Lorentz invariant, it's locally SO3 invariant. It's locally isotropic, at least for ideal hydrodynamics. And also there is no curvature term, it's basically hydrodynamics with a cosmological constant. And the cosmological constant is coupled to via an equation of state, basically. I'll give another talk about this. But the whole point is that hydrodynamics is a poor people's general relativity, and local equilibrium also gives you local equilibrium also gives you a constraint which has nothing to do with the unitarity of the system. It comes from the unitarity of the system plus the buff, but it's much more general than the unitarity of the system itself, which is what are called the Kramers-Koenig relations, that every correlator has a real and imaginary part, and they're related using some kind of dynamical relation. So in a mix, so what I'm saying is that one could think about quantum gravity in a very similar way that one could think about what do statistical fluctuations and quantum fluctuations do for a fluid. What role do they have in a fluid? Which is actually another unsolved problem. No one has actually solved it, and I'm working on this mainly. And this is sort of the reason why I started one of the reasons I started thinking about the quantum gravity issue. But it's sort of a much simpler problem, and there is some experimental data, heavy ion data with highly fluctuating fluids. So basically, what I'm saying is that if you give up on canonical quantization and think about mixed systems from the beginning, you might be able to implement a strong equivalence principle using dynamical Kramers-Kronig relations. Being slightly more specific, a Lagrangian can never be background independent in the bulk, but if you have a bulk and a boundary, so if you have a bulk and a horizon, and if you always have a source term which is coupled to the bulk, if you always have a source term which is coupled to the bulk, which is the fluctuation term I was talking about, you might be able to construct a theory that obeys general covariance where unitarity is substituted by a fluctuation dissipation relation. The fluctuation is going to be the system detector back reaction, and the dissipation is the Gibbons-Hawking term, and the dissipation is the Gibbons-Hawking term. Physically, it basically means that you're going to have a quantum system which is back reaction with a thermal bath, and which is also back reacting with a detector. This is not unknown physics. This is something that we sort of know how to develop. And incidentally, I mean, recently there was this idea which was covered by the press quite a lot, and they wrote a PRX, where basically they claim that they have a consistent, I mean, we always knew that quantum mechanics, we always knew that for consistency, if matter is quantized, gravity has to be quantized as well. Otherwise, you will get faster than light quantum propagation. You will violate the no signaling criterion. But recently, there was this proposal by Jonathan Oppenheim, which basically says that perhaps a quantum theory and a stochastic theory together are consistent. What I'm saying in practice is actually similar, except I'm not saying gravity is not quantized. Gravity is quantized along with everything else. It's just that the way observables are defined, observables have to be defined if the strong equivalence principle works. If the strong equivalence principle works, you have to define observables in a way that obeys general covariance. And that basically means always having open quantum systems. This basically means having always having open quantum systems. And the effective theory might actually be similar to Oppenheim's effective theory. This is speculation. I mean, please don't think that I have a theory in development. I'm trying to put together the criteria that a theory should have. However, we did think about possible consequences, and I have some published results using possible consequences, and even results which are experimentally detectable. We proposed investigating fluctuation dissipation relations in strongly accelerated charges in synchrotron accelerators. And this is not just an experiment. This is an experiment that can be done in Campinas because, of course, we have a cyclotron light source. And this is ongoing work in collaboration with them. And I mean, the idea isn't to investigate quantum gravity, but the idea is to investigate to what extent in this case, the electron is our observer. The electron is our semi-classical observer. And we want to see to what extent its stochastic motion can be understood using a Brownian motion effective theory. There is actually a class of theories which is excluded from the effective theory. And intriguingly, for example, a term which can never be covariant is the theta term of QCD, which experimentally happens to be zero. So this general covariance, the fact that the effective theory is generally covariant, provides a new way of thinking about the strong CP problem. Perhaps the right effective theory to describe our universe is generally covariant, and that precludes a QCD theta term, and this is sort of the solution of the strong CP problem, and there will be no axions. There is a relationship with holography because the effective theory is going to have a bulk term and a boundary term which are correlated, and in certain limits they will decouple, but they're still correlated. They're still constrained. They're not correlated. They're constrained. And perhaps holography is a manifestation of the strong equivalence principle valid at the quantum level, and I wrote about this. And this is actually a good place to stop. And I would just like to say that quantum gravity research was always seen as this is where all the smart people go, but also the people who are sort of out there, because real physics is about experimental data, and this is a purely theoretical endeavor. In fact, we have a hope. It's a hope, it's not a certainty, that you are going to have a golden era for science, because the questions I'm asking are highly conceptual, but I want to stress that they are sort of semi-realistic experiments which are being thought about, which might shed light to some of these questions. And there might be surprises in these experiments. So conceptually, I think that the big question was asked, it's not renormalizability, it was asked by Bronstein in the 30s. And this is the question that we have to address. And if these experiments are going to produce answers that basically say that when quantum gravity is relevant, the system is always mixed, we might need to start thinking about an effective theory where the strong equivalence principle, which is quantum, but the strong equivalence principle is built in terms of density matrices. And this is a good place to stop. Thank you very much.
Thanks, Donato, for the very nice talk. We have some time for discussions. Does anyone have any questions?
Again? Yeah. For those who are really interested. Yeah.
Does anyone have any question? Quem quiser fazer a pergunta em português, fiquem à vontade também. O Donato
eu queria falar em inglês, mas posso responder.
Não, eles podem fazer em português, mas você responde em inglês ou em português, o que você preferir. Tá? É só para o pessoal não ficar tão envergonhado só. Alguma pergunta? Fiquem à vontade para abrir o microfone e fazer pergunta.
So either I blew everyone away or everyone thinks I'm crazy.
Perhaps both.
Perhaps both. It's in a superposition.
Yeah, I have one question to kick off some discussion then.
Mm-hmm.
Well, actually, it's a comment. I don't understand when you say that you can have general covariance at the level of the correlators. Because, for example, you could quantize gravity using the background field method, mm-hmm. and then you get some effective action, for example, that is fully quantum and also generally covariant. So there's no problem with that. So I'm not so sure what you meant when you said that.
Yeah, good point. And my answer is this: that you can, but wait, where is the right slide here? On the slide, here it is. Yeah. So you can do gravity as an effective theory, and your background field method should reproduce the effective theory results. I mean, at least I think it should. Hmm. And for example, the effective theory results, and this is the Donoghue paper that I cited, in particular say that to one loop, deflection of light by gravity is going to depend on the particle spin. So you have a gravitating body. You have a gravitating particle, I should say. This is at the level of a single particle. It's a purely theoretical calculation. So you have a scattering of a graviton and a photon. Sorry, you have a scattering of a certain particle and gravitons. And what is going to happen is that to one loop, the deflection of light by gravity will depend on spin, will depend on the properties of the spin. So the one loop effective action is not just going to be R, it's going to be R times other things. And this would essentially mean that this equality that I put in, that the energy momentum tensor defined in terms of the Lagrangian and the energy momentum tensor defined as in terms of the graviton vertex function, are not the same. So if this is the case, if this is the result that you obtain by the background field method, like at one loop, so the effective Lagrangian isn't going to be simply L equals R plus matter, but it's going, or FR plus matter, but it's going to mix R plus matter, then you've then it will no longer be true that correlators will be generated by metric transformations.
But these other terms that get generated at the level of the action, they're still invariant, right? Under diffeomorphisms, I mean.
Yeah, but well, I mean, the point is, let's say, that's the thing. I'm defining the equivalence principle in terms of correlators, or sort of physically. Let's imagine Galileo on the Tower of Pisa throwing stuff down the Tower of Pisa. So if your effective Lagrangian is going to be gravity, it's not going to be R plus matter, but it's going to be 1 plus, it's going to be R times a function of a scalar field or a function of a fermion plus matter. Then Galileo throwing that fermion and another fermion of the Tower of Pisa, the two fermions will not have the same path. The two particles will not have the same path.
Yeah.
And in terms of the formula that I have above on this slide, that's what I'm saying. It will not be the case. The equal sign will be invalidated. So yeah, you have general covariance at the level of the Lagrangian, and this is a big point. You can certainly have general covariance. The general covariance at the level of the Lagrangian and the general covariance at the level of correlators is a different thing. I'm defining the equivalence principle at the level of correlators.
Right. Yeah. Because as far as I remember, if I recall correctly, this paper of Donahue, what they did was to show that there is some small violations of the equivalence principle, but in the sense that the particles no longer follow geodesics, and occur space-time. But that's like a very, very small violations. You could, sure. You could average out, for example, and still have some trajectory.
No, look, I mean, as far as I'm concerned, physics is an experimental science. What I like is that the experiments I was talking about really might be able to prove the equivalence principle at the quantum level. If particles don't follow that's what I'm saying. I mean, sort of correlators have to follow. My definition of the equivalence principle is that correlators have to follow geodesics.
I see.
And if that's not the case in your favorite quantum gravity model, then as far as I'm concerned, you're breaking the equivalence principle. It doesn't mean you're wrong, because no one has tested this.
Okay.
Yeah, and I also don't have consistency. I'm simply trying to think about what the equivalence principle looks like at the quantum level.
Right. Yeah, thanks. Any other question? I have another one, if you don't mind. People aren't asking, so it's a general question. I suppose you know those people that work with those experiments. So did you have any idea on so how far are we from testing these things? Are we talking a decade, 3 decades, a lifetime?
I know the theorists advertising this, and they're all very keen. The experimentalists are talking about technical. I've looked at talks of these experimentalists, and they give technical details, but they haven't given a timeline yet, as far as I know. Come to São Paulo at the end of September, and maybe quite a few of these attendees are not quantum gravity people; they're nanotechnology people.
Right.
And I will ask this question in September as well, right? Yeah.
I'll certainly be there.
I can tell you that they're interested. I mean, because usually if you propose something to an experimentalist that is undoable, they will just laugh and not pay any attention and talk about theorists being stupid. They're not. I can tell you that much. I mean, they're taking it seriously. Yeah.
We have time for one more question. So apparently you don't have any.
Thank you for your attention. Muito obrigado.
Ok. Então a gente pode parar por aqui. Donato, muito obrigado pelo seminário. E espero você aqui em Curitiba, quando você estiver por aqui. Você
vou estar lá
que a gente conversa sobre física.
Você tem gente que queira conversar